So unit 3 is about dynamics. So kinematics is all about motion of objects. In that particular case, we're just trying to describe the motion of objects. Okay, so we're not into explaining why. So we didn't explain why a projectile will follow that particular path or trajectory. We didn't explain why an object will be moving a straight line unless you try to force it to stop or what. Okay. So now to explain the motion of objects, that is actually in the dynamics part. So when you say dynamics, this is the explanation of the causes of motion. Causes of motion. And we will try to explain why objects behave that way using mainly the 3 Newton's laws. Okay, and an important quantity when we try to talk about dynamics is the quantity force. Force can just be defined as a push or a pull. Okay, and it is considered as an external influence that can change the state of motion of the object. And the SI unit is Newton. So for force, automatically, if we're talking about force, we use that particular unit, which is Newton, or represented by capital N. Okay, and Newton is actually a derived unit. 1 Newton is considered as equivalent to 1 kilogram meters per second squared. So later on, we will try to define the significance of a Newton. This is not part of your, I didn't include this one in your note template. However, this can be found in your textbook, okay? I want to include this one because in this particular unit, you'll be encountering these forces, okay? And an integral part of understanding this particular unit is to identify these particular forces, okay? So let's say, for example, for friction. So for friction, usually we use the symbol F sub F. And remember that force is a vector quantity, by the way. So this is a vector quantity. So it has both magnitude and direction. Okay. So friction, by definition, is a contact force. So when you say contact force, that means that the two forces are, well, in contact with one another. Okay. And it acts to oppose the sliding motion between surfaces. Okay. And its direction would be dependent on, well, it's always parallel to the surface, but opposite the direction of the sliding motion. Okay, so that means that for friction, that means that if you have a surface, so this is your surface, and if you have an object on top, okay, so let's say, for example, the velocity of the object is that way. So it's moving in that direction to the left. Friction in that particular object would be to the right. So this would be FF. Okay, so just to denote that this is a vector quantity, their force must be there. So if you have another drawing, and again, this is your surface, if you can see, that's parallel. So parallel to the surface. So that is the meaning of that one. These two are parallel with this. So parallel lines. Okay. So the friction is always parallel to your surface. Okay. And let's say, for example, that object is now moving to the right. So friction now would be in the opposite direction. So friction would be here. Okay. So what you're gonna do if you want to identify the direction of friction, well, you just try to identify the direction of your motion, the direction of velocity, or the way it is moving. If it's moving to the right, friction would be to the left. If your velocity is to the left, friction is in the other direction. And if you can see here, again, friction is always uh, parallel to the surface. So it's a contact force. That means that they are in contact with one another. So it could be, well, a box or another box, still creating friction there. And for the second one here, normal force. So actually, these are some common forces that you'll be encountering here. So when we say normal force, again, it's a contact force. So that means that the two objects must be in contact. It is the force exerted by a surface on an object. And its direction, take note of the direction also, it's always perpendicular to and away from the surface. So therefore, if I have an object, this is my object here, and it's lying on the surface, the normal force is just going up. So your normal force is just this one here. This is your Fn. Okay, and if you can see, it's always perpendicular. Well, thinking about the surface, that one there. So it's away, always away. So if your surface is here at the bottom, so normal force is upward. And if you reverse, as long as, if you can see here, it's perpendicular. Okay, so make no mistake about that this is perpendicular to and away from the surface. So it's kind of different with your friction, because friction is parallel to the surface. This one is perpendicular. When you say perpendicular, again, it is 90 degrees from your surface. So that particular symbol, this particular symbol means perpendicularity. And spring force, well, not necessarily a common one, but if we're going to talk about the Hooke's law, we'll be encountering this. So it's a restoring force. Excuse me. It's a restoring force. It's either a push or a pull of a spring that is exerted to an object. So I think everyone have played a spring, right? So if you have a spring at home, you can try it out. If you're gonna stretch it outward, you can feel that the spring is trying to pull you inward. Okay, so its direction is also dependent. It's dependent on the displacement. So displacement means if you're gonna stretch it out, or you try to press it down, because if you're going to press it down, the spring will also try to push back up outward. So try to take note that same thing with friction here. Spring, the direction of the spring is dependent on the displacement in this case. And another common force that you'll be dealing here is tension force. So it is just a force in a string, a rope, or a cable. Okay, and its direction is away from the object and parallel to the string, rope, or cable to the point of attachment. So usually, let's say I have well, this is a object, and then I have the string downward. Then let's say, for example, I have an object being attached here. So if I gonna look at here, there's a tension from there going downward. Okay, so again, the point of attachment is this one here. Let's change it color there. So the force is downward. That would be my Ft. But again, this is looking at this particular point. However, if I'll be looking at the other point, this one here, if I'm looking at the point of view, my reference would be the object itself. The tension is actually in the opposite direction. Okay, so again, this is looking at the object being attached to the string. So Ft is, if you can see, it's parallel and away from the object, okay, from the point of attachment. So that is tension. And thrust, although this is just a general term, sometimes generally we just call it as applied force. So it's a force that move objects such as rocket planes or in your cars, the engines, or the people that is pushing the car. Sometimes we just call this one generally as force applied. Okay, if it is not very specific, or if it's not friction, if it's not normal force, if it's not tension force, so we just use Fa, or the applied force. And in the same direction as the acceleration of the object, barring any resistive forces. Okay. So again, if you try to push a table, your applied force there is, let's say, wherever the object is moving. Although there's friction there in the particular case, but the acceleration, if you try to push the object, or if you exert a force that is greater than the friction between the two surfaces, it will accelerate in the direction of your applied force. And lastly, this quantity here, the weight. So this is a long distance force. Okay, so this is just the gravitational attraction between two objects. Well, if you're talking about objects here on Earth, so we use the Earth and the object, and its direction is always straight downward towards the center of the Earth. That's why if you have an object and then you're gonna identify the force of gravity is always downward. Okay, so that is your Fg. It's always downward, and any object on Earth is always acted upon by the force of gravity. So later on, I started with this one because later on you'll be doing what you call as free body diagram. Free body diagram is just a diagram that shows all the forces acting on the object, and that is very essential when talking about dynamics, the free body diagram. Are there any questions so far with this one? These are just definitions. I, I, I won't ask you to memorize this, but it's always good to familiarize this one, because if you mess up in the place in your free body diagram, the different forces acting on the object, well, for sure, your answer would be incorrect. Again, in this particular section, in this particular unit, we'll be talking about forces, net forces, and this is very essential. Although one thing is for sure, you'll be dealing with with gravity. Gravity is always directed downward, and that's already a given. Okay, so an object is always acted upon by the force of gravity.